Hi everybody, welcome to Neuromatch Academy Day number 7. Today we're going to talk about modern convolutional neural networks and transfer learning. My name is Alexander Wicker. I'm a professor of data science at the University of Göttingen in Germany. My lab studies visual perception and brains and machines. We work at the interface of computational neuroscience and artificial intelligence, and we use methods from machine learning to study both biological vision and computer vision. Yesterday, you learned about convolutional neural networks. You learned about how the convolutional operation works, about pooling and downsampling. You learned how to train conv nets, and you looked at data augmentation and dropout. Today, we want to switch gears and learn about conv nets in the real world. As you may know, we can do amazing things with images these days. For instance, we can detect and classify individual objects and images. Object detection and classification is not the only example. Conv nets are really everywhere. For instance, we can do image segmentation. We can also do human pose estimation. Or we could turn photographs into artworks to show an example of our own work. So these examples that I just showed you, they're really just a small subset of what's possible today. And the success of these deep learning algorithms in solving such image recognition capabilities has really been driven by two key factors. First, large-scale convolutional network architectures, and second, an approach called transfer learning. And this is why we're talking about these things today. So here's our agenda. We'll go through the history of conv nets, then we'll talk about the ImageNet large-scale vision recognition challenge, really the breakthrough of deep learning. Then we will discuss how the field has developed deeper and larger models, and we will discuss the concept of transfer learning. And finally, we will look at face recognition as one example, and some of the ethical implications that it can have. I want to start today with a brief recap. Yesterday, you learned about the convolution operation. So to remind yourself, when we process images, we're dealing with very high dimensional inputs. Even a relatively small 32 by 32 image consists of 1,000 pixels. If we flatten this image into a vector and we process it with a fully connected layer with the same number of output units, this layer would have about 1 million parameters. So the convolution layer mitigates this problem by not connecting each input neuron to each output neuron, but instead limiting the connectivity of an output neuron to a small region in the preceding layer. So that means if we're working with a 3 by 3 convolution kernel, for instance, each neuron's activation depends only on the 3 by 3 region in the previous layer. And then we're taking a linear combination of these 3 by 3 pixels activations. So here we have a 3 by 3 filter plus a bias, which means 10 parameters. And then we're not learning these 10 parameters for each location, but instead we're sliding the same filter over the entire image. So if the input has more than one channel, for instance, a color image has 3, the filter kernel would have 3 times 3 times 3 parameters plus a bias. Now in a convnet, we don't only perform one convolution, but instead we carry out multiple of these feature operations in parallel. So we might add a second filter kernel, here shown in red, that generates a second feature map. In general, the convolution layer takes a number of feature maps as inputs and produces a number of feature maps as outputs. We sometimes also call these feature maps channels. The number of channels in the input and the output doesn't have to be identical. So in general, the number of parameters in a conv layer is given by the number of input channels times the kernel size times the number of output channels, plus one bias per output channel. And because in a convnet the weights are shared across space, the number of parameters does not depend on the image size at all. So this allows us to scale up the amount of information processing in these networks tremendously without creating networks that have billions of parameters and would not be trainable. So for the exercise, I want you guys to recap just how massively convnets reduce the number of parameters. We'll count and compare the number of parameters in different convnets and fully connected networks.